that I was studying. So I went out and I got this book. Everybody, if you were going to be doing this kind of research, this was the book that you had to have. And so I was working through, various theorems and trying to learn the subject. And there's one spot where I got to a fairly important theorem, and working through the proof, I got to a spot and I said, I cannot figure out how he got this particular spot. And I circled it. This is back in, a long time ago. Right, circled that in the book. That circle's still in that book. And so as part of this project, we're working through this theorem, and Zoe was able to figure out where that thing I thought was a typo. She actually figured out the entire proof and put it together. So she figured out details that I was either unable to or too lazy to figure out what the details are. So Zoe's done a great job in putting together what should I call this? A major starting point to the field of geometric group theory. She's been able to sort of assimilate all that information, put it together into one very nice thesis. So here we go, Zoe. What are we going to call this? Groups of non-positive curvature?
Yeah. All right, so today we're going to be talking about geometric group theory and solving the word problem for a specific type of group which exhibits non-positive curvature. So in order to just go into some historical background about where exactly geometric group theory comes from, we start, geometric group theory is born out of what's called combinatorial group theory. And combinatorial group theory, briefly put, is the study of groups which are defined in terms of a generating set and a defining set of relations. And so the first main result in combinatorial group theory comes in 1882 when Walter von Dyck gives a systematic study of group presentations. From then, we move to the sort of next large result relevant to us, comes in 1911 when Max Dane, who at the time was working on problems in low-dimensional topology, he realizes and publishes in his 1911 paper that the problems he was working on were in fact just special cases of certain problems from group theory. And so he recognizes this in his 1911 paper, and then in 1912, the next year, he publishes a new paper where he poses his three decision problems. And so these decision problems are the word, conjugacy, and isomorphism problem. Today we're going to be focusing on the word problem, which in brief essentially asks whether or not a word which exists in the free group on a generating set A represents the identity in our group. And so Dane was able to solve the word problem for groups, or for the fundamental groups of closed orientable structures of genus at least 2. And so he was able to do this by exploiting the negative curvature of these groups. And so this idea of curvature is going to come up a lot in solving the word problem for different groups. So his solution to the word problem in these groups was later called Dane's algorithm. And so, although he was able to solve the word problem for one sort of specific class of group, in 1955, Pyotr Novikov finds a class of groups in which the word problem is in fact unsolvable. And so this sort of opens up the question to geometric and combinatorial group theorists of which groups have a solvable word problem and which ones do not. In Dane's solution to the word problem for the special type of groups, he used a lot of geometry in his proofs, and so this sort of foreshadows later developments in the field. But his geometric methods for solving problems in combinatorial group theory weren't really appreciated or expanded upon initially. And so the next result we see comes in 1933 when Van Kampen gives a way to graphically represent words which equal the identity in the group, gives a way to graphically represent words which equal the identity in the group, and these are called, this sort of graphical representation are called, later given the name Van Kampen diagrams. And so then, working off of Van Kampen's discoveries in 1960, Martin Greenblinger is able to show, he uses Van Kampen diagrams as well as to show that the word problem is solvable for groups which meet his small cancellation conditions. And again, the small cancellation conditions sort of, if a group meets small cancellation conditions, we again have this sort of negative curvature, and so he exploits this negative curvature again. So up until this point, we're sort of in combinatorial group theory, and then in around the 1980s, that's too low or too high. In the late 1980s and 90s, we see the sort of distinguishment of geometric group theory from combinatorial group theory with the work of Gromov, whose results are a large part of what I show in my thesis. And so in the late 80s and early 90s, Gromov introduces the notion of cat-zero spaces, which are a special type of metric space, which again exhibit non-positive curvature. And he, in papers that he writes in this sort of era, he formalizes ideas from Schwartz in 1955 and Milner in 1968, who Schwartz and Milner showed that groups which act properly, co-compactly, and by isometries on length spaces can be identified as having the same sort of large-scale structure as the space on which they act. And so, working off of Gromov's work in 1995, Alonso and Bryson publish a paper called Semi-Hyperbolic Groups, where they are able to show that groups which act properly, co-compactly, and by isometries on cat-zero spaces in fact have a solvable word problem, again using the non-positive curvature of cat-zero spaces in order to show this. And so this result is the main result of my thesis and the one that we'll sort of go over in very brief detail today. So now that we have a little bit of background, we need to build up the notion of a free group in order to understand exactly what the word problem is. So in order to build up the idea of a free group, we just start with a set A, which for example here, today we're going to say our set A is just A, B, C, D. And then we also take, in addition to the set A, we also take A inverse, which is just the formal inverses of A. And so these are just sort of extra symbols. They're not, A inverse don't cancel each other out in this point. At this point, these are just extra symbols. And so when we take A union, A inverse, we call this set the set of letters. And then using this set of letters, we are able to create words, what we call words, by just stringing together, create words using strings of letters. Okay, so we create words by just sort of juxtaposing letters from A union A. And so then what we can do is we can think about the set of all words that come from letters A union A. And so we call this set the free monoid on A. And this is given the notation A star. And in addition to having just this set, we also equip this set with the operation of juxtaposition. So we have a set, we have an operation, but this set with this operation doesn't quite yet form a group. We have an identity, which is just the empty word. We have associativity because juxtaposition is associative. However, we don't yet have inverses yet because juxtaposing two words together is only ever going to increase the word length. So if we want to find inverses, just using juxtaposition isn't going to allow us to do that. So we need to sort of create inverses by expanding upon this free monoid on A. And so we do so by defining an equivalence relation tilde, which is defined by the word W is related to the word Z if, actually no, getting ahead of myself here. So if we want to find inverses, what we need to do is remove, sort of take these A inverse and stuff like that, and have them actually cancel out. So we do that by defining what canceling pairs are, which are just subwords or substrings of x inverse, or x inverse x. And so we call strings like this canceling pairs. Furthermore, we say that a word W is reduced if there are no canceling pairs present. And so now we can define an equivalence relation tilde on the set A star, the free monoid on A, by saying that W is related to Z if we can get from W to the word Z by only removing or adding canceling pairs. And so once we take this set A star, the free monoid on A, and we quotient out by our relation tilde, which can be shown is in fact an equivalence relation, then we finally now have a group where we actually have inverses now. And so this group is called F of A, which is read as the free group on A. And so this sort of idea of a free group is, it gives us the sort of minimal constraints necessary to create a group. And so this free group is free of any relations. It allows us to combine words from F of A in really any way we would like. And so, yeah, so we have a lot of freedom in how we can combine things. So from the free group, we can then, by adding restrictions onto the free group, we can then create new groups. And so we do this by dictating that certain subwords are to represent the identity in our new group. So we do this by, we call these subwords that we say represent the identity, we call these relators, and we notate this set as the set R, and these are just, R is the set of words which equal the identity in our group. And so, if we take the free group and then we take out one sort of like natural assumption of how we can create groups from the free group as well as a set of relators would be that maybe we would take the free group and then quotient out by the set R. However, this does not form a group. This isn't quite what we want, because if we just remove relators, then we might end up with canceling pairs left after those relators are removed. So instead, what we need to do is quotient out by the normal closure of R, which is the smallest normal subgroup containing all elements of R. And so it can be shown, and I show in my paper, that in fact the normal closure of R is equal to just the product, or the set of products of conjugates of relators. Wi, Ri, Wi inverse, such that Wi is in F of A. So the normal closure of R is just equal to products of conjugates, which are these Wi's, where Wi is just some element of the free group, and then Ri is some relator. And so now we finally have a group. And so if we have some gamma, which is isomorphic to the free group on A, mod the normal closure of R, then we say that gamma has group presentation angle bracket A bar R. So if we have some group which is isomorphic to the free group on A, mod R, then we can just write gamma as equal to A bar R. It can be shown that every single group, in fact, has a presentation. And so this is really what the heart of combinatorial group theory gets at, which is just the study of groups using these group presentations. So once we have this group presentation, we can then view our group as a metric space using the presentation. And so this is where we sort of move from combinatorial group theory to geometric group theory, because now we're looking at our group as a metric space. So in order to define a metric on the group, we first define word length. And so we write word length. We write, to represent word length, or the length of word W, we write absolute value W. And this just equals the number of letters needed to write W in the free group on A. And so then using word length, we are then able to create, induce a metric on our group gamma. And so we define the word metric for a group gamma equals presentation A R by the distance, using the distance sub A, because this is our generating set, of the distance from the word W to the word Z is just going to equal the minimum word length of the minimum word length for all x and f of A, such that x is equal to WZ inverse in gamma. So we take all words in the free group on A and then find the minimum word length of all these words where the word, or where x is equal to WZ inverse in our group gamma. And so yeah, now we have a way to sort of represent our group as a metric space, and this allows us to do a lot of really interesting things. And so now we can sort of understand what exactly the word problem is asking, or what the word problem is. And so the word problem asks, does W in some word in the free group on A represent the identity in gamma. And so being able to show that a certain word is equal to the identity in our group, in fact, is only necessary to show that this word lives in the normal closure of R because we've got this quotient group. And so a word equals the identity in gamma if and only if it is the product of conjugates of relators. And so all we have to do is decide whether or not it lives in this set. Of course, this is quite difficult, and this is sort of what boils down to how we end up solving the word problem in different groups. So for my problem that we end up, or for the word problem in the groups that we are considering, we consider group actions, which applies the symmetries of a group to a set. Today we only really consider groups which act on metric spaces. We also only really consider groups which act properly, which essentially is just saying that the orbits of elements aren't too close together. They don't stay really close to each other. So we need the action to be proper. We need it to be co-compact, which says that there's some compact set that when you apply the whole group to it, it'll equal the whole space it's acting on. And then finally we need our action to be by isometries, which is just a distance preserving action. And so we'll be able to see and show that gamma, which acts properly, co-compactly, and by isometries on a geodesic space, in fact, we can view our group gamma as having the same large scale structure as our metric space, or our geodesic space X. And so just to go sort of briefly brush over what exactly a geodesic space is. So a geodesic is the sort of a generalization of a straight line from the Euclidean plane to a general metric space. And so a geodesic in a metric space is a distance minimizing curve. Furthermore, we say that a metric space is a geodesic space if for every 2 points in the geodesic, or in the metric space, if they are connected by a geodesic, then we call that space a geodesic space. And so, although we can't quite, it would be nice, but we aren't able to show that gamma, which acts properly, co-compactly, and by isometries on a geodesic space, we can't show that gamma is isometric to the space on which it acts, but we can show that there exists a map which goes from gamma to our geodesic space X, which scales distances plus a margin of error. And so if such a map exists, then we say that gamma and X are quasi-isometric. So they're sort of almost isometric, but not quite. And this is sort of this idea of like having the same large scale structure. And so this result, and so showing that a group which acts properly, co-compactly, and by isometries on a geodesic space X was first shown by Schwartz in 1955 and Milner in 1968. And so this is called, aptly named, the Schwartz-Milner lemma. And so this is a pretty important result in my paper and as well as in geometric group theory in general. And so the Schwartz-Milner lemma, the statement of the lemma goes, if we have gamma acting properly, co-compactly, by isometries, on a geodesic space X, then we have that gamma is finitely generated. And not just gamma is finitely generated, but furthermore, we have that the map, which takes gamma to gamma dot x naught for x naught in our geodesic space X, is a quasi-isometry. And so, again, like I mentioned, this is a very important result. And luckily, I'm able to give a little bit of a sketch of how this goes, a sketch of the proof. And so, using the fact that the action is co-compact, we can say that there exists a compact set C, subset of X, such that gamma applied to C is equal to the whole set X. Then we let x naught be an X and D be a real number greater than 0, such that our compact set, which allows co-compactness, or which demonstrates co-compactness, is a subset of the open ball centered at x naught of radius d over 3. Okay. Furthermore, using the fact that the action is proper, we can show that the set A, which is all elements of gamma, which take, or all elements of gamma, such that gamma applied to the open ball centered at x naught of radius d intersect the regular open ball centered at x naught radius d not equal to the empty set. We can show that this is in fact finite. And so all that remains to show is that the set A generates gamma, and then also as well as the quasi-isometry. To show that this set generates, what we do is we take the point x naught, and then we take the point gamma dot x naught for just some general gamma in little gamma in gamma, and then we draw the geodesic which connects the two. Okay, so we've got a geodesic from x naught to gamma dot x naught, and so then what we're going to do is we're going to break up this geodesic into d over 3 sections. So we have some x1, call this point x1, call this point x2, x3, dot dot dot, xi, dot dot dot, xn minus 1. And so this distance is d over 3, this one will be d over 3, exactly d over 3, this one, so on and so forth, up until this one will be d over 3, and then since the distance from x naught to gamma dot x naught is most likely not a multiple of d over 3, this last little section is going to be less than or equal to d over 3. And so then, using the fact that the action is co-compact, what we can do is we can draw sort of d over 3 balls around each xi. And because the action is co-compact, we know that we have some point within this d over 3 ball around x1 where there's some gamma 1, which when applied to x naught lives within d over 3 of x1. And so we're able to show that this is true for all xi. So we can write gamma sub 2 dot x naught, so on and so forth with this xi. We get the general gamma sub I dot x naught. And so we have all of these gammas which take x naught to the d over 3 ball within whichever subscript it works, or it corresponds to. And so then once we have all these gamma sub i's, we also let gamma sub naught equal the identity, and then gamma sub n equal just regular gamma. And so what we can do is, using the triangle inequality, we can show that the distance from gamma sub I dot x naught to gamma sub I plus 1 dot x naught is less than d, because we're within d over 3, go another d over 3, within d over 3. So, since we act by isometries, this then tells us that the element gamma sub I inverse, gamma sub I plus 1, in fact lives in our set A, because we have taken things less than d away. And so now what we can do is we can write gamma as equal to gamma naught inverse, gamma 1 inverse, gamma 2, so on and so forth, up to gamma n minus 2 inverse, gamma n minus 1, gamma n minus 1 inverse, gamma n, where each one of these things in parentheses is, we've shown, is an element of A. And so now we can write gamma in terms of generators, and so then we are able to show that A in fact does generate our set gamma. And so now we have a generating set, a finite generating set for our group. And so all that remains to show is that we have a quasi-isometry. And so what we can do to show this, I'll just have to do it over here. Identify a map which takes elements from gamma, brings them to x, and which scales distances plus a margin of error. So, using this sort of picture, we can show, or we argue that n minus 1 times d over 3 is less than, strictly less than, the distance from gamma dot x naught to x naught, because we've broken this up into n minus 1 d over 3 sections and one section that's more than 0 but less than d over 3. And so then a little bit of algebra tells us that n is strictly less than 3 over d times the distance from gamma dot x naught to x naught plus 1. And so we can also, since we've written gamma as a word of length n from our generators, we can show that n is equal to our, with a scaling factor of 3 over d and a margin of error of 1, we end up with a quasi-isometry between, or quasi-isometric embedding from gamma to x. And so now we can conclude that gamma and x are in fact quasi-isometric. And so this sort of result is, as I've mentioned, very important and sort of gets at the heart of geometric group theory, because we've used geometry in order to come up with an algebraic result. So we use this sort of geometry of our space to show that the set A generates, as well as showing that the large scale structure of gamma and x are sort of the same. Yeah, so this is a large result. In order to, or in my final result of my paper, we consider groups which act on classes of metric space with non-positive curvature. And so normally the curvature of a space is defined in terms of the derivative. And so not all spaces have a derivative easily defined. And so what we can do is, instead of figuring out like necessarily the exact curvature of a space, we can compare the curvature of a space to the Euclidean plane, which has zero curvature, and use that to sort of compare curvature of different spaces. And so we do this using what are called comparison triangles. And so if we have a triangle this is in our geodesic space X, a triangle P with vertices P, Q, and R. Then a comparison triangle for this PQR triangle in our geodesic space would be a triangle in the Euclidean plane with points P bar, Q bar, and R bar, where the distance, this distance from P to R is the same as this distance from P bar to R bar, same with this distance, and then same with this final side distances. So all the comparison triangle is one which has sort of the same side lengths. Furthermore, we define comparison points. Which a comparison point, to give an example, would be if we have a point X here on this side length, or on this side of our geodesic triangle, then the corresponding comparison point in our comparison triangle would be something like this, X bar, where the distance from X to R is equal to the distance from X bar to R bar. And so, using these comparison triangles, we are able to sort of compare the curvature of different spaces. And so, in order to do this, we have what's called the cat zero inequality, which says that or if I should say, if a triangle satisfies the cat zero inequality, if for all x, y on our original triangle in X and corresponding comparison points X bar, Y bar on our comparison triangle bar, L bar, the following inequality holds, which is that the distance from X to Y is less than or equal to the distance from X bar to Y bar. So in this picture, it would look maybe something like this. So we have 2 points, X and Y, on our original triangle. And so if this geodesic triangle satisfies the cat zero inequality, then we would need that this distance from X to Y over in our geodesic triangle needs to be less than or equal to this distance X to Y in our comparison triangle. And so a cat zero space is one where for all geodesic triangles, or a cat zero space is a space in which all geodesic triangles satisfy this cat zero inequality. And so the sort of idea that this cat zero inequality is getting at is that triangles which satisfy the cat zero inequality can kind of be viewed as like thinner than their corresponding comparison triangles. And so this sort of gets at the idea of having a thinner triangle gets at the idea of having non-positive curvature, because the Euclidean plane has zero curvature, and so if we're thinner, or not even necessarily thinner, but exactly the same, then we have non-positive curvature in our space. And so, using, in 1995, by Alonso and Bridson, they proved that groups which act properly, co-compactly, and by isometries on these cat zero spaces, in fact, have a solvable word problem. And so this is the main result the main sort of end result that I proved in my thesis. And so I'll just give sort of the statement of the proof, and go over a little bit of why exactly this in fact solves the word problem. So this goes something like, if we let gamma act again properly, co-compactly, by isometries on a cat zero space, then the set A equal to all elements of gamma which take x naught less than, strictly less than or equal to d plus 1 away. So each element of gamma which when applied to x naught takes it less than or equal to d plus 1 away. We can show that this set A generates gamma and that A is finite. Further, we let our set of relators be relators, which is a subset of the free group on A. We can define our set of, or we let R be the set of reduced words of length at most 10, which represent or which equal the identity in our group gamma. Then we can say that a word W equals the identity in gamma if and only if there exists an equality in the free group on A, where we can write W as equal to a finite product, so from I equals 1 to n, of xi, ri, xi inverse, so finite product of conjugates of relators, where our n is bounded by d plus 1 times the word length squared, and our length of our xi's are bounded by d plus 1 times the word length. So this gives us an actual algorithm for solving the word problem, because what we've done is we've given ourselves a finite number of words in the free group to check and see if our word equals any of them. Because we've got this bound on n, we've got a bound on the length of ri, and we've also got a bound on the length of xi. And so not only does this give us an algorithm, this is a quadratic, it grows quadratically with the word length, and so it's actually a fairly fast algorithm compared to some. And so, so yeah, we are able to, solving the word problem for groups which act properly, co-compactly, and by isometries on a cat zero space, just boils down to finding all products of conjugates of relators, where the relators are less than length 10, these xi's are less than d plus 1 times the word length, and we have a finite number of products bounded by d plus 1 times the word length squared. So all we have to do is just check every single one. And so the proof of this is statement of result, or yeah, result. The proof of this is quite detail heavy, and so I'm not going to be able to really go over any of it today. But yeah, so this is the main proof that I show, and yeah, we're able to show that in fact these groups have a solvable word problem. Does anyone have any questions? Yeah.
Do you know how common it is to actually find groups that satisfy these properties?
No, I'm not sure about that. I've really just been working like assuming that they do satisfy these properties.
Lots and lots.
Yeah. Yeah.
Is it possible that gamma itself is a geodesic space? Like, how closely is gamma related to this X? Like, could it actually be a geodesic space and just acting on itself, or?
Yeah, so that's definitely possible, although not necessary, because all we need is that it's quasi-isometric to a geodesic space. But yeah.
So is it like a manifold? Is it, like, what kind of a space is it? Is it like a continuum of some kind of real numbers, or like, or is it like a graph type of space, or is it a
It's like,
metric space?
you can sort of view it as like the Cayley graphs. So that's more so like how I think of it, is we can view the space gamma using Cayley graphs of elements of gamma.
So it's kind of like a graph.
Yeah.
So it has a dimension 1 or something.
Something like that. Okay.
All right, great job. So this concludes the public portion. Everyone except examiners, please exit some period not too far.